I'll take a couple of minutes time to introduce some about ourselves, our company, right? So what do we do? We have three major areas to work in. First is engineering and a process simulation, under which whether it is structural, CFD, thermal analysis, or on right side, what you see is basically a welding simulation or farming simulation, some of the manufacturing simulations as well that we are actually into. We have a product distributions related to these technologies, and we do have services as well in these areas. The second area is tolerance stack-up analysis, ensuring precision in assembly process, and that is the subject matter for today's webinar. So we will anyway talk a little more about it further. And the third area in which we work is production process optimization, under which I mean like first two things, engineering and then tolerance stack-up analysis, that's validation of an assembly. After it is done, once you realize the parts assemblies, we just want to check that, from a quality control QC standpoint, product, I mean, part wise or maybe assembly process wise. So under which, we have couple of hardwares and a software which addresses these requirements. So quality management system under which we have not only a measurement, I mean hardware and software for measurement and collating a data, but to even get statistical process control document, which can basically help us understanding where our processes stand. Okay, so to address these three major areas that I showed earlier, these are our strategic partners. 3DCS, that's what basically brings geometric dimensioning and tolerance analysis software. The 3DCS is the name of the software. The company to which this particular software belongs to is DCS, Dimensional Control System. It can help us handling assembly variation. It can help us doing tolerance optimization, which can help us minimizing repair, reverse, rejection, etc. And I believe this is the only software which can actually account for thermal and mechanical loads. In the sense, majority of the tolerance stack-up analysis tools basically can handle all the component as rigid component, whereas given a situation in practical environment, some of the component you may probably want to have flexible so that you will be in a position to accurately capture the variation. So these are some of the functions that DCS has. Anyways, we will see that in more detail further. Hexagon is essentially the some of the products that you would be knowing. Nastran, Adams, and all basically belongs to Hexagon now, and they're into multi-body dynamics, structural simulation, CFD, thermal, acoustic. You name the solver, and it has it actually. Then some of the solutions which can address manufacturing simulation, like welding simulation, metal 3D printing, and so on. It has got software to handle autonomous driving and material characterization and so on. Then the third strategic partner that we deal in is Dynaform, which is sheet metal farming simulation solution, which can help engineers to do permeability simulation to nesting, in order to optimize the uses of the material. It can help engineers to get optimum blank size, die face design, progressive die design, tube bending and forming. And after you basically make your die model ready, it can as well help you to do a CAE simulation of a die structure to understand if it is going to withstand the load for which you have designed it. Then the last but not least, the strategic partnership we have is with Tridiagonal Software, which is essentially, and the software is made essentially to handle mixers and reactors. So mixture design and reactor design, this particular software is made up for. It can not only help us getting the fine-tune process parameters, but it can also help us to see detailed 3D vortices with the help of CFD solution to understand how the whole mixing process is happening. That's about it. Thanks for your attention uh, for the company introduction. So before we get in today's topic, let us understand why dimensional engineering uh, is required, or let us understand how cost and quality basically work. So if you look at these two curves, quality issues uh, from left to right, the quality issues are being reduced. Whereas when we are reducing the quality issues, manufacturing cost is going to go up. That's very simple, uh, you know, mm, understanding. If we leave a lot of quality issues in the product, we will have a risk of performance failure, risk of warranty claims, product non-conformance, and so on, right? Which the stage which we don't want to be there. At the same time, on the right side, if you have taken care of quality issues the most, whether they require or not, um, you would probably land up in the zone where your product will be costly, risk of not being price competitive. So, as an engineer, we have to actually strike a balance between both of that, quality issues and manufacturing cost, and that's exactly where technology like 3DCS come in. Now, designers will always have some of the questions when we design part, subassemblies, and assembly. So when we define some datum, whether the selected datum is appropriately defined or not, we won't be knowing unless we validate. Obviously, with an experience, you can always decide certain level of information in the model. Is the selected assembly sequence right? Again, what is my mating plane, four-way locator, two-way locator? Something that, again, designers will basically go by their judgment. Which component to be given more importance? I mean, yeah, in order to understand in my assembly, which sub-assembly or which component should be given more importance, that is also one of the challenge and a question at that stage, engineers will have. And let's say any component which we feel is important, what dimension and tolerance in that particular given component is going to be very, very important. Rather, it is going to contribute the most of the variations that are actually coming at a location of interest. Again, pretty simple question. All the tolerance equally important. Obviously, when we study it thoroughly, we may find that all the tolerances are not very important for the functionality which you have designed your assembly for. And then finally, how to find major contributor and bring assembly within acceptable limit. So all these are the question challenges that engineers work with, and 3DCS brings answers to these challenges. It determines how part and assembly tolerances affect the overall build and a fit of product. Whether I'll be able to build the assembly in the first place, you get an answer to that. If you get the assembly get built, how good it gets built, how well it is you are able to build it. Where should I measure in a production? In the sense, this can as well help you understand uh, the QC methodology that you need to follow. Where will I have manufacturing problems specifically? So once you understand the sensitivity of every tolerance or dimension in the assembly, um, you can easily understand what manufacturing process you need to follow or what sort of problems you may probably face. How will tooling affect my product? In case in your assembly you are using jigs or fixtures, you can as well model those in the 3DCS environment and understand uh, because of fixtures or jigs, your assembly is getting hampered. Yeah, and again, because you are doing all this validation virtually, you always have a choice to do a lot of what if study in order to determine if your assembly process that you are following is correct. If not, you can actually follow something else and try and do reduce variation. And finally, based on contribution and based on sensitivity of given tolerances and dimensions, you will get a lot of insights in order to reduce the problems or maybe fix variation issues. All right. So 3DCS is CAD-based tolerance and process analysis software, which can get integrated into any of your CAD platforms like Katia, Siemens NX, ETC Creo, SolidWorks, and so on. In case you don't want to use TDCS within any of these mentioned CAD platform, then we have a CAD neutral standalone version called TDCS Multicad. So because I don't have any CAD platform available on my laptop, the demonstration that I'm going to do is on Multicad only. These are some of the global users who use 3DCS predominantly, and the list is much bigger. Just to show you in under each and every domain, that is aerospace, automobile, heavy engineering, medical devices, electronics. I mean electronics and consumer goods manufacturers. You have all big names that are actually we see around every every now and then. Mercedes-Benz, Valeo, Volkswagen, uh, General Motors. On this side, Indian OEMs like Tata Motors, Mahindra and Mahindra, Ashok Leyland, and so on. They use 3DCS, make use of 3DCS, and they're continuously improving build quality and assembly gap and plus requirements. Okay, so with that, without spending much time, we will get into the software and understand how software can actually be useful to you. For that, I'm just taking one simple demo example in which we the objective is to determine variation in the gap between headlamp and a tail lamp, turn lamp. I'm so sorry, headlamp and turn lamp. Both of them are actually getting mounted onto the bracket. So you can see the assembly is only having three components: headlamp, turn lamp, and a bracket. The objective is to measure gap between both of them. Again, nominally the gap is 6 mm, and specified limit for gap is plus minus 1.5 mm. That means gap can go up as much as 7.5 mm maximum and as low as 4.5 mm. That's with that objective. Let's move on to uh, the software. Okay. Uh, Before I start that example, I'll just quickly show you an environment. The starting point in 3DCS is your nominally build assembly. Uh, what I mean is, as far as assembly goes, you have appropriately build it without any interference and without any wrong placements, is what nominally build assembly is. Now in this particular environment, multi-CAD environment, I start with import CAD model, uh, and you have a lot of options to bring in. You can bring in IGS, STEP, JT, and so on and so forth. Obviously, there are all CATIA, UG, ProE, all those models also can be imported in Predicius. Once that import is done, in order to build your model for doing tolerance stack analysis, you are only supposed to define some of the things like moves, that is nothing but assembly relations, tolerance and GD&T, and measurement. Measurement is measurement that I basically showed you earlier, right? The gap between turn lamp and headlamp is the measurement requirement. So once these three things are done, your problem is ready to solve. So pretty few things only. This is just to define your problem. And if you look at GD&Ts that we generally follow, you can see almost all the type of GD&Ts that we generally use. 1 minute. Okay. So you can have a look at the different types of GD&Ts that you're allowed to give here. I'll probably use some other model so that my system does not get slowed down. Okay. So datum you're able to define, able to define size tolerance, position tolerance, surface profile, flatness, perpendicularity. Um, as per ASME, all these tolerance GD&Ts that basically people apply. Now, typically, if you get in any of the tolerance, let's say position tolerance, okay, you, anyways, since I had basically selected the topmost assembly, um, it is taking much more time. So, anyways, so we just need to mention the feature, mention what is the tolerance level. If you have minimum material condition or maximum material condition or something, you can mention that, and you can mention, uh, datums frame. Okay, like ABC with respect to ABC or AB, whatever number of datums you want to basically define for that particular frame. So anyway, I'll to explain these things, I'll be in a little simpler one so that it takes a lesser time. So these are the things that you will be able to define. Again, when I say move, uh, that means the relation between the component, right? For example, this particular assembly, if you say, see, these are the flat surfaces of the pin which go on flat surface of the bracket. That is primary relation. Then these pins, cylindrical pin goes in the holes on the bracket. That's how the assembly is happening. So there are different type of assembly method. Um, Most of them, which are very frequently used, basically define our assembly based on 3-to-1 principle. I'm sure you must be aware of that. What it means is first relation basically help us locking 3 degrees of freedom, then 2, and then 1, so that my the assembly is fully constrained, kind of. Okay, so that is how the assembly relations are given, and then you can define measurement. For example, you have facility to define point-to-point measurement, surface-to-surface measurement. You can as well define, just I want to understand any point location, how much it is varying, and so on. Angle, clearance between pin and hole, all sort of measurements can be actually defined. Once it is done, this is just a visualization tool. For example, my nominal build assembly, after I define the relations, this is how it is basically getting defined. But in case of a very large assembly, you would also want to understand if assembly sequence is appropriately happening. So you can animate and see, how those assemblies are actually going to take place. Yeah. So this is just to animate that. And now once assembly is done, I have a choice to see, how my components are, uh, behaving. Assembly is behaving. So this is just based on whatever clearances you have in the assembly relation, and whatever tolerances, for example, position tolerance of this hole and pin, profile tolerance of all these surfaces, and so on, based on which it can actually show you tentative variation that can basically happen. However, the detailed variation can be calculated later. Now, I'll just quickly show you an example where you may require only a single assembly, but that assembly you need for a different configurations. For example, this is not a right example, it is just a rear seat. But front seat, you would understand that you will have a configuration of the seat when it is straight, or maybe it is reclined by 30 degree, or it is reclined by 15 degree, or something like that. So you don't have to actually build multiple assemblies in that case. So that is where model variants facility is there. So you can have a single assembly. You don't have to define all tolerances, JD&T in every configuration of the assembly. You can simply create those model variants here. So that is how it is made to handle many different types of situation that we mechanical engineer face during the assembly. Okay. Uh, Now, once it is done, it is just simply to solve it. When it comes to solver, it is Monte Carlo analysis, which basically 3DCS do. That essentially is very well-known algorithm for handling a lot of permutation and combination where it happens. For example, when I'm mentioning number of builds here, maybe 2000, 5000, or whatever numbers you want, it means the every tolerances that you are defining, in those many steps it can actually make samples, and permutation and combination of those components, it can actually make 5000 number of samples of this particular assembly. That's what it means, right? So let's say if I just quickly solve it, um, yeah, it is. You understand that these are the three measurements that we have asked for, and you can go ahead and start checking how my assembly is behaving when it comes to upper gap. So let us understand where that upper gap is. Okay, here. This is where the first measurement is. Okay. So what it shows now. Uh, Obviously, the nominal was 6 mm. You were saying, the limit that is given on lower side was 4.5 mm and upper side was 7.5 mm. That's what it is showing. And here it is estimated one. So what can go? I mean, how low it can go when it comes to that particular gap? 2.9 is the lowest one it can actually calculate. 9 point. I'm so sorry. 1 minute. 9.11 is the highest gap it can actually go there, right? So what is the total variation? Difference between both of them is 6.2. And what is the percentage of samples which may go out of the spec? So these are the specification limit. On upper side, what is the percentage of samples going out? On lower side, how many percentage of samples uh, how many percentage samples are actually going out of the spec? So that is what it is showing. Now, let us assume whatever is the reason, whatever is the number of samples going out of the spec, what is the reason behind that? So that is nothing but contributor. So it is suggesting us, okay, this is the topmost contributor it has. It also says that surface profile, it belongs to bracket, If I simply open this and just show you what that particular tolerance is, so that is essentially a surface profile of the bracket, is the topmost contributor. Then it says hole position on the bracket is another second contributor. Then surface profile on uh, measurement surface. Yeah, the measurement surface here. So that is third level of contributor and so on. So it suggests you the sequence of the contribution, percentage of contribution that is happening because of that particular tolerance. Also, it shows you geofactor. Geofactor is nothing but sensitivity. How sensitive this particular measurement is to a given tolerance. For example, surface profile, I mean the measurement, upper gap measurement is 3 times sensitive to any variation that is happening on surface profile. If this profile changes by 1 unit, whatever it is, 0.1 mm or whatever, gap can change by, let's say, 3 times to that particular variation. So that is what geofactor is, geometrical factor. Now, if you see this geofactor is too high, what could be the reason? That if my uh, four-way locator or a two-way locators are appropriately placed, or it may so happen that you are measuring the gap. I'm so sorry. 1 minute. How can I? 1 minute. Huh? Sikkim. Okay. Okay. So let me build that. I'm sorry, I just forgot what I was explaining. Anyway, so um, now if I'm measuring over here, that is my measurement location. That is top gap here, and my four-way locator, let's say, is very much away here. Assume that's not the right strategy, isn't it? If you want to maintain a proper gap here, the locators that you are using, I mean, this could be best locator, so that immediately near to the measurement itself, you are locating it appropriately. If this is your area of concentration, area of interest, then why to put your four-way locator away from that? Something like that. So that is the kind of insight you get out of this result. Now lower gap also, again it will list you number of contributors, its percentage contribution. Obviously here range it suggests you, if C stands for clearance, HP, that is whole pin. So this particular contributor come from a whole pin relation of turn lamp and bracket here. So that clearance is creating, that becoming a top level contributor, right? Now, for example, here you just observe there are around 7.5 and 7.17% samples are actually going out of the spec. Now, understand that the surface profile given is one range. Let me just go ahead and make that as a 0.5. Just experiment, and nothing. Obviously, you will always have a choice how much you can go down based on manufacturing process that you follow and all. So that's all different thing. Here, just for sake of changing, I'm just changing this value, quickly rerunning it again after I made that range to zero point 0.5. Okay. Now, upper gap, first of all, one observation is the samples which were going out of this spec has reduced drastically from 7.5 to 5.2 or something. And the uh, surface profile of the bracket was contributing, coming as a topmost contributor, that is coming at around sixth location now. So some other parameters became a more contributor, I mean bigger contributor than that, right? So that is the kind of what if studies you will be able to carry out. Now once your design, I mean the analysis is done, you can automatically extract the reports, uh, generate report in HTML, Excel, PPT, Word format. You can generate in any format, but HTML being my favorite one, I'll just create that. 1 minute, let me just put it properly so that see it captures the image that is actually appearing on the screen whenever you do that, those things, right? So let me generate the report. You can always choose what to take, what not to take in the report. That's your always choice, user's choice, right? And it nicely brings up the report. If you have a model summary, it will automatically appear here as to what is your model, what is the reason behind solving this particular problem, and so on. You can mention that, and this is analysis region. So we have only done it for three measurements. Where that particular measurement is, when you hover the mouse, it automatically brings up the picture, logo gap, minimum gap, and so on. If you want to see details, you can click on it. You see normal distribution with whatever percentage out of the spec going. Then you can go ahead and see contributor analysis, which will list down the contributor. And when you click on any of the contributor, it can show you what that particular contributor means. Where it is, where that particular feature is. Surface profile. Yeah, this is what it is showing you. This is second contributor. So you can see that in detail, right? And everything is actually linked with each other. Then, what was my complete model input, like assembly sequence? What was the assembly sequence in the sense the moves that we have defined? Turn lamp to bracket, headlamp to bracket. Then what was the GD&T or tolerances? You can see them from part to part, every part, this all belongs to bracket. Then you can go to headlamp and see what are the gradients that you have defined. Complete detail at single page. And you can see it's a detail in the next page as well. That is how it is. Then even measurements also. So there are only three measurements, but you can see where those measurements are. All right. All this you will be able to get in the report. As well, you can get complete component information. Uh, which are the component you had, how many components, how many points were there. Complete summary of the model you get here. You get tree structure. I mean, this is pretty small, but otherwise, if it is large model, it is very important to see actions tree in terms of GD&Ts, datum and size tolerance, and component wise, every component you can get it in tabulated format. And finally the analysis setting, where your input file was, what was the summary in terms of number of parts and GD&Ts and so on, um, and all other solver detail. It also provides you complete sensitivity analysis setting. So you get complete summary here. When was it solved? Where the file was saved and so on. So complete thing you will basically get in the report. So very detailed report actually you get in any of the format that you choose. So HTML basically has got all linked, so that I use that particular form. Okay. Uh, Now, once I obviously before I solve, I would have already defined the measurement and GDNTs and all. I can actually view them component wise. Even when you are simply hovering the mouse or just clicking on it, for example, this particular tolerance, the profile tolerance, see, it is applied on these many surfaces. Position tolerance is actually applied on these pins, see, holes, sorry, holes. So the moment you hover mouse onto it, it can actually automatically highlight where this B datum is applied to this hole, size tolerance is applied to this hole. Okay, this particular pin, the size tolerance is applied. Yeah, position tolerance is applied. So that is how it is. I mean, when it comes to validating the model.
Hey, hi, Kushal. Yogesh here.
Hmm.
Sorry to disturb you. Maybe you have been talking for some time now. Maybe
Hmm.
to take a 1 minute break, I would like to ask the audience, is there any questions or is there anything you would like to see it again or anything of that sort? Just to make maybe a half a minute or a minute break.
Yeah. Okay.
Uh,
If you
if
have
any,
any questions in between, you can ask me before we move on to the next.
yeah, I mean, if anyone really has a questions, please put in the either chat box or maybe raise a hand so that we can unmute so that he can speak.
All right. So this was one of the demo example that I wanted to show you. Obviously, these were the GDNTs that were defined on the
Mr.
model.
Mr. Nrupat Yadav have raised a hand. Maybe
Okay. Yeah.
just a moment. I'm
Can
just
you
opening.
help me with
Yeah, yeah. So the
the
this
question that
this
he
is
has?
open.
Hmm.
Yes, Mr.
I'm
Nrupat.
just unmuted.
Hi
I'm
Kusal.
so sorry.
Hello, sir.
Hi Kusal.
Tell me.
Can you hear?
Yes, yes, I can hear you, sir.
Yeah, Kusal. Actually, here was the mock drill, so I joined it late. So can you just quickly
No.
brief me?
Okay.
Yeah,
See what you want to understand, sir.
from the starting, you just quickly brief me. In short, this is how we can, in which software it is compatible, and how we can use it.
Okay. 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 Perfect. Perfect.
I hope
So,
you already given
no, no
the
problem. No
brief,
problem.
but yeah, please.
Maybe
Thank
maybe
you.
I'll just borrow a couple of minutes from other participants and quickly brief you.
Yeah.
So this is basically a dedicated tolerance stack-up analysis solution. It can actually get onto any of your CAD platforms like CATIA, Siemens NX, PTC Creo, SolidWorks, and so on. It also has got CAD neutral standalone version. That is what I am actually using when doing demo. So it can equally well fitted into the any of the CAD environment, and beyond. I mean, the input which it requires is just assembly, and over and above any other information that you basically want to put onto the individual component, you will be able to put them uh, in terms of assembly relations, in terms of GD&Ts and tolerances, and finally your area of interest where you want to measure it. So what I was actually showing, if you have just arrived, what I was showing is the simple flow from importing the model to define the basic information which are required for the tolerance checkup analysis, uh, just to visualize those things and solve and report. So this is where I reached. Okay, it's pretty simple environment, for mechanical engineers to understand. After I solved, I was just showing a report which got generated automatically. It's quite detailed report which basically provides you uh, complete understanding about particular measurement and to those measurements, which are the contributors. For example, this particular upper gap. it is varying this much. All these readings are actually given on top, and it can give you contributor. So whole position was topmost contributor. Then you have surface profile and so on and so forth. So this was the report that I was actually showing. Hope
Okay, got it. Thank you.
you got glimpse
Mhm.
of it, right, sir?
Yeah,
Right.
yeah,
Okay.
yeah,
In
yeah.
the interest
That's
of
it.
time, otherwise you can reconnect us anytime, sir. We can have a detailed discussion. Okay. All
Of
right.
course. Yeah.
Yeah. So these were the simple models that I have actually used in the demo. So these are the typical part level tolerances that are actually defined. We have taken them onto the 3D model in 3D environment. But yes, if you say you are using PMIs in NX or FTA in CATIA, where you are already defining GD&Ts and tolerances in the part level itself, then you will be able to reuse them in 3D environment, 3D environment. You don't have to recreate them again. Not only GD&Ts and tolerances, but you will be in a position to use even the constraints that you have given uh, in the assembly. I will just quickly show you an example. Anyways, before which you have already seen the typical output that 3DCS provides. It does Monte Carlo simulation. It provides you quality matrices like PPK, CPK values, which basically makes you understand where your process stands. Key contributors by which we understand which GD&T and tolerance are contributing to a variation. Percentage out of spec, looking at which you may probably take decision whether they are acceptable percentage or not acceptable percentage, depending on the assembly that you deal with. What is the total range of variation that it is showing? If it is acceptable, it is okay. If it is not, what needs to be done based on contributors and its sensitivity? You can do a what if study. That is how it is. Geofactor is nothing but sensitivity, we can say in a simpler language. So how much does the part geometry contribute to the uh, product's variation is what geofactor means. Okay, so I'll just quickly show you the demo in NX actually. Okay, so this is NX environment in which one simple assembly is imported. When it is imported, you can see the tree in 3DCS is simple. In the sense, they are only parts. So there is no tolerance, there is no moves. Okay. Yeah, you can see on the top the same set of uh, icons what you have seen in multicad are seen. Okay, these are the parts in the assembly, right? So if you look at the screen, you have all the GD&Ts and tolerances are defined in the NX model. Yeah, you can expand the. I mean, I have expanded the tree and shown you this is how it is. Uh, every individual component also. I mean, if you just go in the component level and see, yes, all the GD&Ts are actually defined. Okay, so here it's very simple. We can just update. Uh, yeah, we just got into the assembly. We can just update the model once before we want to bring in all these PMIs that are defined in NX environment. Yeah, here extract GD&T. Can you see extract GD&T? Okay, so let me update the model first, and I'll say extract GD&T for all the components. So I'm just choosing top level and said okay, these many. No, this is not extracting GD&T. This is basically defining the moves. So relations that you have defined at the assembly level, like mating, hole to hole axis alignment, and so on, it basically brings that as a move. However, you can always make changes in those moves later. Yeah, you can see the animation, how moves are getting defined. Yeah, bush and the bracket got onto the base. And this is the complete assembly that is made. Now, earlier, as I explained you, move, GD&T and measurement, out of which move is already defined. Now we can actually move on to let me just fast forward it in the interest of time. So here we would like to just extract the GD&Ts automatically from PMIs that are defined. So if you expand any of the components, see, let me just uh, sort them automatically so that datum, size tolerance, and all other type of tolerances will come in sequence properly. So A datum, B datum. So this process has extracted the GD&Ts from PMIs defined in the model. Now, once the GD&Ts are defined, you can see, I'm so sorry, profile tolerance on this particular surface is applied. So let us see the variation at the surface level itself. See, because of the profile tolerance defined here, you can see that surface is varying. To visualize that, I've just made the mesh on. And this is like, after defining the relation between parts and defining the tolerances, this is tentative variation, kind of a model basically breathes. This is how it is breathing. And then you can solve it. So that is how simple it is when it comes to your given CAD environment. However, even when you are using multi-CAD version of the software, you will be able to import the this information like GD&Ts and moves. These are the modules of the software in which what we have seen is variation analyst, which is topmost one. But we have very small and a simple module called a design variation modeler, which is kind of a replacement to 1D stackup that people do quick. It should be used by majority of engineers, and then maybe a specialist GD&T person can basically go for VA, variation analyst. So that is how the functionalities are actually bracketed here. Yeah, I mean, this is what I basically wanted to show. Say, so DVM, design variation modeler, can be used by designers quickly. Each and every sub-assemblies and assemblies that you deal with. Then engineering team, where you have uh, mechanisms to deal with. Mechanical variation modeler, basically when you have a kinematic joints involved in the assembly, you can make use of it. And VA is kind of a specialist where you can do a detailed tolerance stack-up study. All right. We have couple of add-on functionalities which can also be used, but they are add-on to variation analyst to handle certain situations. Just for an example, this FEA compliant modeler essentially to account uh, for a deformation in parts causing less, I mean, because of deformation, it basically the measurement may be a less accurate, so that you don't have to worry about once you use that as a flexible component. Over constraint assembly, parts deforming or has more than 3 primary datums, clamping sequence, welding, bring back issues, gravity, all these situations you can use FEA compliant. So this particular example you can easily understand. Now this hood or a bonnet being a very large component, you can see because of the gravity itself, the portion is a little bit bending, exaggerated in actually showing that, but that is how it goes. So obviously, because of the self weight, the gaps that we are actually measuring across the length of this front length of the hood, it may not go uniform. So how can we control that? first of all, the accurately measured gap needs to be considered this component as a flexible component. That is where FEA compliance comes in. Sometime when you are fixing components on fixtures for welding it, so you are clamping them, and after you remove the clamp, obviously it springs back. How much spring back will happen? All those you will be able to see. This is another example of gravity itself. So if you just snap this rear bumper at both the ends, left and right ends, and maybe in between couple of snaps, still because of its self weight, the variation you will see, gap you will see will be different. I mean, in the middle, it is going to be definitely larger compared to what you measure on either end of it. Sometimes thermal. Uh, any situation you measure the gap, you may find it different because of the thermal environment. All right, so I mean, in the interest of time, I am not going to show you all the add-ons that we have, but yes, I mean, depending on your requirement, we can explore them further. Just to show you guys examples, any practicalities that you want to basically consider in the model, like for example, the type of moves that we were seeing, the assembly sequences that you were seeing, primarily, even when your pin distance and hole distances are not matching, but because all four holes to be somehow assembled, that is what practically happens. Then you can use a move called pattern move, right? So it just overwrites onto the primary move, and finally the pattern move will be used for solve. So that is how the keenly all type of actually assembly relations are defined. And any size of assembly you would want to capture variations, you can take into account different assemblies and sub-assemblies that we can think of, not only in automotive, but elsewhere as well. So if you look at this main assembly, there are lot many sub-assemblies, the bracket going onto it, another bracket going onto it, and so on, right? So that is how the assembly is taking place. Once it is done, whatever your measurements are, like my measurement here is distance between these holes, distance between these holes, vertical distance between the hole where the latch is coming and from the base. In short, when we assemble this onto the vehicle floor, all other locations where I'm supposed to reach, I should be able to reach it. Otherwise, it does not make sense. You install this seat on the floor, seat assembly on the floor, and when you start latching it, the latch pin is elsewhere and not matching here, not coming here. In order to ensure that, we have to ensure that the variation between floor and this particular pin location remains within the tolerance, so that I'm able to assemble them. That is the exact purpose, why people use tolerance stack-up analysis. Yeah, I'm done with it. I mean, if you have any questions, you can ask me now.
Hi Kushal.
Yeah, tell me.
Can you show one example with calculating the worst case scenario for any dimension which you already having? So
Right.
that will.
Right. Okay. Obviously, when I'm saying uh, this variation analyst, it essentially does Monte Carlo simulations, and what we say normal distribution, or um, Six Sigma, things like that. Worst case scenario generally, when you measure things manually. For example, here, uh, you basically build the loop, right? This particular measurement, you will have, first of all, what is the distance between this bracket and this thing, then this outer bracket to outer bracket, right? And then this outer bracket to this particular location. That is how you build a loop.
Correct,
And
correct.
you actually go all plus is the worst case on plus side, all minus is the worst case on minus side. That's how you do.
Mm.
That also can be done, but that does not serve the purpose. See, basically, if you go with the worst case analysis, a majority of the times the assembly that you reject may not
Uh,
get.
we can't hear you, Kushal.
Yeah.
But yes, I mean, the answer to your question is it is
Actually,
possible.
Kushal, we lost you in between for 5 seconds.
Oh, is it? Okay.
Yeah.
So what I said is, worst case scenario is something that we will not be interested in, but yes, in Solver you will be able to do a worst case analysis also.
Mhm. So the worst case scenario is okay, means that is exactly completely worst case. And
Correct, correct,
in this you have a different Monte Carlo method.
correct, correct,
So
correct.
we can get both the values like Monte Carlo method, how the variation will come, and the worst case scenario also will be there, so that we will have the
Yes,
both the things there. So that,
correct,
can
correct.
you just give one example, like you are saying that the left and right bracket having, so in between that you already provided the input about the geometrical the tolerancing. If
Hmm.
you have in this or other example you have, then that will be better. Uh,
Okay. Okay. Uh, Worst case definitely will have a different results. Um, I have not done carried out worst case analysis here, but then we have user DLL for carrying out worst case study. We need to check the DLL for that, appropriate DLL for that, and solve it. It can provide you worst case study.
mhm.
However, this particular assembly, or any assembly for that matter, here we have already solved this. So I will just show you results for this as well. This only.
Okay.
So like for each measurement we have a normal distribution within plus minus 3 sigma, that is total 6 sigma. Okay,
Mm.
what it shows is lowest side it can go the gap which is currently 6 mm in the assembly
This is
nominally.
nominal. Mm.
Nominal can go as low as 3.2, as high as 8.83. Okay, and when it is varying so much, this much, which are the contributor that they are contributing to this variation, and what is the percentage by which they are contributing to it.
Mhm. Okay,
Also
so
provides you
this is
sensitivity.
Monte Carlo method, na? This
Correct, correct,
calculation, and
right.
in worst case scenario, it can go more than this.
Huh. Correct.
Correct.
So 1 minute more or less depends, 1 minute. Huh? Anup, hello, Anup is there. There is a straight away one quick run for worst case scenario which we can actually run it in through DLL. I can actually suggest you. I mean, I can show you that as well, sir. So I can show you the difference between Monte Carlo simulation and worst case. Once you have this, you will not be using worst case. But yes, I mean, for your information, to calculate the way you calculate the loop and get the worst case result, you will be in a position to get it in 3D also.
Okay.
Yeah.
Okay, so I just wanted to see the complete means this 6 nominal and other worst case. So which is you have considered which geometrical tolerances considered in that. So that loop I wanted
Okay.
to see in
First of
this.
all, okay, huh. First of all, here, since it's a 3D model, right? Now
Mm-hmm.
we have defined GD&Ts
On the part level.
wherever we have defined it. Okay. Now,
Yeah.
um, we don't have to really worry about what GD&T it is basically considering when it is measuring this particular gap. Okay. Software
Mm-hmm.
will automatically define that. Sometime some features, for example, this is oblique feature, right? This will
Mm-hmm.
contribute you in flush as well as gap, isn't it, sir? Yeah, because it is oblique,
Mm.
uh, it can contribute to gap that is horizontal as well as flush that is vertical difference, isn't it? This alone, this particular surface that is oblique. So when you make manual loop, that time it becomes very difficult to consider it's a sine and a cos component of this particular factor. Am I right, sir?
No, so
So,
this yellow,
so
yellow and red, both the part is going to assemble on the blue part, blue
bracket, correct, correct,
bracket. Oh yeah.
right,
So in this, you have the screwing feature on the bottom side, screwing
correct,
or
correct,
guiding. Guiding is
correct.
not there. I think directly screwed. You are going to
Yeah, yeah.
screw,
It
huh?
is just a guiding features actually, or maybe through
Oh,
whatever
oh,
you consider.
okay, so the guiding feature variation also considered in your calculation.
Perfect, perfect. So any
Uh,
tolerances now, I mean, if I just have to show you the just simple
Dimension, yeah.
deviation, yeah, any deviation that you have between hole and pin also will be taken into consideration. Plus, plus because of the profile of the surface, whatever gap is coming, that is also getting counted. Or not only that, I mean, it is not only about the clearance between hole and pin, but it is about position of this hole, position of this pin.
Tolerance,
Right, right.
variation
All
of the
this
pins, whole.
exactly, exactly.
Mhm.
Now, when we list the results, you can understand based on the contributor which are the most used in that particular
Contributing.
loop. Based on contributor,
Mhm.
you will understand how it is basically making the loop, right? So this is whole position. Whole position on the bracket will definitely impact gap, isn't it? Then
Yeah.
surface profile. Surface profile means this measurement surface only. So any profile tolerance that you're applying on turn lamp and surface profile applying on headlamp on this particular surface is directly contributing to the measurement. 1:1, right?
Mhm. Yeah, yeah, clear.
Correct. So that is how it takes. So you don't have to worry about how the loop is going to come. Acha, in case
It is
you're
it
not
is just on us. We can how
correct,
we are
correct.
providing the tolerances and
Right,
how
right,
we are
right.
uh, using this
In,
software.
in,
So
in
this
case in
software
case you
application.
have not defined all the tolerances and you don't want to define all the tolerances, but appropriately what are required only you want to define, then you can make use
Hmm.
of this relationship, okay, wherein it says, let's say some tolerance, let me remove because, uh, particular feature. Now, any feature that you see, if they are used in the assembly and tolerances are applied, then no errors. Tolerances are applied, but they are not used. No problem. That is not a bad situation to be in. But any feature which does not have a tolerance, but they are used either in a move or a measurement, will highlight you red, so that you are supposed to think, okay, there is something missing in it, right? Example, this particular
Mhm.
hole should have a position tolerance, right? So let me just remove, if I can, refresh it. it shows this feature is used, but not tolerance. Yeah, it's a simple, right? I mean, if you are using it in assembly or in measurement, that is not going to be ideal feature, no? It should have size or a position tolerance to be defined. So once you go through this relationship, you will automatically understand for a given model definition, if there are any missing things, you will be able to just validate them quickly. That is when
Okay.
you don't. I mean, you have not defined all the tolerances in the model. That you just want to take up what is required to start with. Then this is good way to see. I hope you understood this
Okay.
point.
Yeah, understood. So this environment is completely for 3D CX, 3DCS.
Correct.
So we can import the file CATIA, UG, any file we can
Correct.
import here,
Correct.
or a
Correct.
step
Correct.
file
So
also we can import.
yes, I'll just show you the formats. So you have obviously all CAD primary
Step
CAD
followed it.
formats like CATIA, UG, ProE, SolidWorks, and as well as neutral formats like IGS, STEP, JT. You can as well import, for example, majority you don't have a CAD model for, and you have
Scanned file.
Hello, Kushal sir.
okay.
Hello.
Vishal, we are losing you in between.
Hello.
Yep, now it's okay.
Hmm.
Anyway, you were asking for Anup,
So these
Kushal.
are the
Anup
different
is,
formats that hmm.
you were asking for Anup, Kushal. Anup is here unmuted.
हाँ कुशल सर
अच्छा
यस
नहीं ठीक हाँ हाँ Anup, just I wanted to carry out quick worst case analysis for which what DLL file do we use?
so in the
Do you recall
function
now?
name yes in the function name in the
हाँ
drop down you have to select the DCS simu by model the first one
one
itself
minute हाँ Simu
first one
this
simu
one
by
only first
model
one only
हाँ
okay
yes
ठीक है
yes
ठीक है ठीक
and then
है okay
click on the run function button
run function okay okay hmm. So it automatically shows here huh. So hello huh. uh, 1 minute I just forgot Yadav sir.
Yeah. Yes, Kusal.
Right. Right. So I've just carried out worst case analysis, which automatically shows the report as well. So estimated high here, it is taking 10.97 and the lowest is 0.97. So this is worst case analysis. The range is 10 mm.
Mhm.
Yeah. For a
Yeah,
second
maybe
measurement
this
distance.
this value maybe due to change due to you have deleted something.
Correct. Maybe possible. Yes. Yeah. It may not be as big difference as what you see here, but yes, I
Mm-hmm.
mean,
Yeah, I got it. Means
yeah,
this feature is available, like worst
yeah,
case
yeah, it is.
also we can get from here.
All right. Okay.
Hmm. Because sometime we don't have any choice. We have to go with the worst case analysis only.
Okay. Yeah, you can do that. Not an issue, sir.
So that is related to the severity only.
Mhm.
If it is less severe, we can go with the other method, which is
Mhm.